Uh, my name is Corbin Anderson, and for our project of Complexion, we did ours via capillary electrophoresis. So, basic background of what is capillary electrophoresis. Electrophoresis is a process in which ions move with applied voltage. Ions move from the positively charged anode to the negatively charged cathode. This process creates an electroosmotic flow across the thin glass capillary tube. As the buffer flows across the capillary tube, it carries an analyte with it. The data that the capillary electrophoresis kind of gives off is a absorbance over time graph that you can see on the right. The x-axis is time in minutes, and the y-axis is absorbance in 214 nanometers. Pros and cons to using this method. The cons of this method are the thin glass tube is prone to breaking, especially with this instrument. This instrument gave very many low coolant errors which interrupt the automated processes. The data files seem to be stored as DAT files, which are unreadable in Excel and other Microsoft products. So the only way to really get the graph off of it, I found, is to take a picture of it and just crop out the undesirable information. Pros of this method is that with small sample sizes that reduce waste. The instrument can be programmed to run automatically, so you can program all your tests, leave it set, and if everything goes good, then it'll run each test and give you all the data at the end. And the data comes out in a nice, neat graph that's already made for you. The procedure for this is pretty simple. All you have to do is rinse the capillary out just to make sure no contaminants are in there. This is just used with water and 0.1 millimole and sodium hydroxide. They're just rinsed through with pressure. Just make sure any particles are just out of the capillary. And then your desired analyte is injected for 10 seconds at 15 psi, and then the buffer is ran through at 20 kilovolts for 5 to 10 minutes. And this just allows the buffer to carry itself, carry the analyte through and pass the detection window, which gives us our graph.
So for the results, this is a sample graph from the absorbance versus time we get from the capillary electrophoresis. The specific graph is R pseudoephedrine in buffer B. The absorbance here is at 0.035 AU and it's at 3.30 minutes. And this data table shows the peaks K and delta G for all the trials that we ran, but the delta H and delta S were not able to be calculated because the entirety of our experiment was ran at 25 degrees Celsius, so there was no variance in temperature allowing for calculation of delta H. So this experiment, the expected outcomes were to calculate delta G, delta H, and delta S for beta cyclodextrin and RNS pseudoephedrine. The literature values, respectively, are negative 11.33 kilojoules per mole, negative 4.1 joules per mole, and negative 12.54 kilojoules per mole. The experimental outcomes, we got negative 9.25 kilojoules per mole with 18.36% error, and 1.08 kilojoules per mole with 109.5% error for the R and S delta G values, respectively. And we did not have a delta H or delta S calculation, so there was no percent error there either. Possible sources for error in the delta G comes from preparation of the solutions, calibration of the capillary electrophoresis, and calculations and use of the equations throughout the experiment. In the future, it would definitely be beneficial to implement variance in temperature to allow for calculation of the delta H and the delta S. And it would also be beneficial to vary the actual conditions in which the solutions are prepared. The capillary electrophoresis is ran to determine the ideal conditions for the complexation. And in conclusion, delta G for R pseudoephedrine and beta cyclodextrin was negative 9.25 kilojoules per mole, and the delta G for S pseudoephedrine and beta cyclodextrin was 1.08 kilojoules per mole, with percent errors of 18.36% and 109.5% respectively. The delta H and delta S were not able to be calculated due to a lack of variance in temperature, and delta H relies on a change in temperature, and then delta S relies on delta H to be able to be calculated. The significance of these results theoretically demonstrates the free energy change that occurs during the complexation of beta cyclodextrin and pseudoephedrine, and possible improvements moving forward would be for an emphasis on calibration, preparation, and calculations, as well as a variance in temperature to calculate delta H and delta S, as well as to determine the ideal conditions for the overall experiment.